Let me put two numbers side by side. The ant covers 1 centimeter per second. The rope it stands on stretches 1 kilometer per second. That is a factor of 100,000. The ant starts at the left end of a 1 kilometer rope and crawls toward the right end. Almost everyone gives the same first answer. It never gets there. But here is the answer. Does get there. Once you accept that what the ant earns each second is not centimeters, the rest is grade school arithmetic. First, the pedigree of this puzzle. All we have is a single line Martin Gardner wrote in his 1988 book. This delightful problem, with a flavor of Zeno's paradox, was devised by Dennis Will Quinn of New Caledonia. It first appeared in December 1972, in the puzzle column of the French monthly Science et. Ant on a rubber rope is a nickname that stuck much later, and in 2018 Vsauce 2 made it a talking point again. At the end of every second the rope jumps by 1 kilometer, all at once. It is stepwise. Reversing the order, stretch first, crawl after, multiplies the time by about 2.7, so we keep the original. The third rule is the key. The ant sticks to the piece of rope under it, so when the rope stretches, the ant rides along. An ant walking on fixed ground would never arrive. That is exactly where the answer flips. One note in advance. The arithmetic uses the stepwise original. The figures use the smooth version. Let's follow just the first second of the stepwise original. The ant crawls 1 centimeter. At that instant the rope goes from 1 kilometer to 2 kilometers, exactly double. The ant is now at the 2 centimeter mark. It walked 1 centimeter and traveled 2. Here is what common sense missed. The stretching also happens behind the ant, on rope it has already crossed. And every bit of that stretching behind the ant pushes the ant forward. Of course the finish line ran away too, so measured in distance the ant is worse off than before. So we change the ruler. We measure the share of the whole rope the ant occupies. A kilometer is 100,000 centimeters, so right after the first step the ant is at 100,000th of the whole. After the rope doubles, it is 2 centimeters of 2 kilometers. Still 100,000th. Uniform stretching changes lengths, but it cannot touch shares. The ant's job is not to close a distance, but to collect shares up to 100%. The figures shrink the numbers so you can follow them. A 1-meter rope, stretching 3 times faster than the ant. The top panel is a real centimeter ruler. The finish line pulls away far faster than the ant. The gap grows from 100 centimeters to 246 at 21 seconds, then falls to 0 at 64 seconds. The bottom panel redraws the same 5 moments as shares. 0 then 34.3%, 66.7, 85.5, 100%. Never once goes down. The 21-second mark, where the gap was widest, is already 2/3 of the way along the lower ruler. What changed is not the ant but the ruler in your hand. The lower ruler had the answer from the first second. Now let's write the ant's earnings into a ledger, second by second. In the nth second the rope under the ant is n kilometers. It crawls 1 centimeter, so the share is 1 over n units. And what the ant must fill is 100,000 times the first second's share. So the arrival condition of the stepwise original reads exactly like this. The sum piling up on the left has a name. The harmonic series. The bars on the left take the first second as 1. They collapse to 1/2, 1/3, 1/4. On the right is the running total, and each step on the horizontal axis multiplies the time by 10. 1,000,000 seconds is about 11.6 days. 11 days of crawling for 14.39 units makes a target of 100,000 look like a joke. Yet there is a way to double this ledger total. Square the number of seconds crawled. By 1,000 seconds it is 7.4855. By 1,000,000 the square of that it is 14.3927. Short of double by about 0.58. That missing 0.58 is no accident. It is the Euler-Mascheroni constant, written as gamma. The ant collects 2.93 in just 10 seconds, so squaring always nearly doubles the ledger. And you can square again as many times as you like. Looking from the other side gives the same result. Name a target and count the second it is reached. To claim the ant fails you would need a total it never reaches, and no such total exists. The ant arrives not because it is fast, nor because the rope gets tired. It is because a ledger of shrinking shares has no target it cannot fill. And yet, for a long time what the ant sees says the opposite. The ant's speed over the ground is the sum of two parts. The second part keeps growing. At 50% progress it gets half the stretch, at 90% it gets 90%. Meanwhile the finish line recedes at a steady 1 km per second, start to finish. So the gap is widest at the moment the ant's true speed equals the speed of the finish line. To catch up it must receive nearly all of the stretch, and the stretch is 100,000 times stronger than its legs. So until it is 99.999% of the way, the ant sees only the target receding. In time though the story changes. The peak sits at 0.3679 of the whole journey's time. That is because pushing progress the last 100,000th needs the rope to grow 2.718 times again. The red curve on the left peaks at 246 centimeters at 21.3 seconds, then falls to 0 at 63.6 seconds. The green dash progress curve laid over it keeps rising without a kink, even at that peak. Progress at the peak is 66.7%. The classic 99.999% is that same value pushed to the extreme. The right figure previews the bill. The time to finish against how many times the ant's speed the stretch is. 3 times gives 64 seconds, 10 times 6.1 hours, 20 times 8 years, 30 times about 113,000 years. Raising the ratio tenfold does not multiply the time by 10. It replaces the number of digits outright. And the classic problem is not 30 times but 100,000 times. Now it is time to take the bill. In the stepwise original, the seconds needed for the ledger to pass 100,000 begin with 1.576. Written out in full, that number has 43,430 digits, and the unit is seconds. So the conclusion has to be written on two levels. The ledger answers whether it arrives. The clock answers whether anyone can watch it arrive. Ask it the other way round. To finish within a year, the ant would need about 208 kilometers per hour. So how slow could it be if we gave it 13.8 billion years? About 89 kilometers per hour. We multiplied the time budget by more than 10 billion, and the required speed fell only by a factor of 2.35. There is a version you can do at home. Drop the ratio to 1 times and 43,430 digits of seconds become 17.18 seconds. Here is the puzzle's hidden control group. Put beside it an ant that walks at the same speed but is not carried by the rope. At the 3 times setting it stalls at 31.7%, just short of 1/3. This contrast shows without a word what that third rule was doing. One more thing. Its speed along the rope never changes. Only its speed over the ground grows. Now the calculation we postponed. What if the rope stretches smoothly? In this version, progress is written cleanly as a function of time. All you need to know about the logarithm here is that it grows very lazily. As long as the length is finite, the share at any instant is never zero and can never be negative. So progress never once goes down. Nothing already written in the ledger gets erased. The moment that value reaches 1 is the finishing time. With the classic numbers it begins with 2.807. Set it beside the 1.576 the stepwise version demanded. Both have 43,430 digits, but different leading figures. The ratio is exactly 1.781. That gamma is the same one that left the doubled ledger short by about 0.58. One last boundary, saying the ant always arrives however the rope stretches goes one step too far. What decides arrival is not how strong the stretch is, but how fast the share bought each second shrinks. If it doubles every second the share shrinks far faster, and the ledger stops at a finite total. The ant's test in one sentence. Does the sum of the shares gained at every instant reach 1? The integral that decides whether light from a distant galaxy reaches us has exactly the same shape. A comoving coordinate is assigned so its value does not change as the universe grows, the same job as the ant's share. The classic stretch corresponds to a universe whose size grows in proportion to time. Such a universe has no event horizon. That is why the ant always arrives. An exponentially growing universe flips it, because the ledger converges to a finite value. The observed universe is accelerating, so it has an event horizon, estimated at roughly 16 to 17 billion light-years. So the conclusion that light from any galaxy, however distant, eventually reaches us does not hold. Conversely, light from a galaxy now receding faster than light can still reach us, because the expansion rate changes. Finally, let's read the number written on the ant's own ruler. In the smooth version with the classic numbers, the ant covers 1.386 centimeters in the first second. Written on the ruler of shares, that same second is about 7 parts in a million. The 1.386 centimeters loses its meaning the moment the rope stretches again. The 7 parts in a million survive any amount of stretching. Nobody takes them back. At the moment the finish line was farthest away, the true ruler reads 43,430 digits of centimeters still to go. At that same moment, the ant's ruler reads 99.999. The ant never gained distance. What it gained was a share of the rope. And uniform stretching can never take back a share already earned. If you enjoyed this video, please subscribe, hit like, and turn on notifications. See you in the next story.